Appendix 2. The Quadruplex and Phonoplex. Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, visit LibriVox.org. Recording by Anna Maria Viola. Edison, His Life and Inventions by Frank Louis Dyer and Thomas Comerford Martin. Appendix 2. The Quadruplex and Phonoplex. Edison's work in stock printers and telegraphy had marked him as a rising man in the electrical art of the period, but his invention of quadruplex telegraphy in 1874 was what brought him very prominently before the notice of the public. Duplex telegraphy, or the sending of two separate messages in opposite directions at the same time over one line, was known and practiced previous to this time, but quadruplex telegraphy, or the simultaneous sending of four separate messages, two in each direction over a single line, had not been successfully accomplished, although it had been the subject of many an inventor's dream and the object of anxious efforts for many long years. In the early part of 1873, and for some time afterward, the system invented by Joseph Stearns was the duplex in practical use. In April of that year, however, Edison took up the study of the subject and filed two applications for patents. One of these applications embraced an invention by which two messages could be sent not only duplex, or in opposite directions as above explained, but could also be sent diplex, that is to say, in one direction simultaneously as separate and distinct messages over the one line. Thus there was introduced a new feature into the art of multiplex telegraphy, for whereas duplexing, accomplished by varying the strength of the current, permitted messages to be sent simultaneously from opposite stations, diplexing, achieved by also varying the direction of the current, permitted the simultaneous transmission of two messages from the same station and their separate reception at the distant station. The quadruplex was the tempting goal toward which Edison now constantly turned, and after more than a year's strenuous work he filed a number of applications for patents in the late summer of 1874. Among them was one which issued some years afterward as patent number 480,567, covering his well-known quadruplex. He had improved his own diplex, combined it with one of the Stearns duplex, and thereby produced a system by means of which four messages could be sent over a single line at the same time, two in each direction. As the reader will probably be interested to learn something of the theoretical principles of this fascinating invention, we shall endeavor to offer a brief and condensed explanation thereof, with as little technicality as the subject will permit. This explanation will necessarily be of somewhat elementary character for the benefit of the lay reader, whose indulgence is asked for an occasional reiteration introduced for the sake of clearness of comprehension, while the apparatus and the circuits are for the sake seemingly very intricate. The principles are really quite simple, and the difficulty of comprehension is more apparent than real if the underlying phenomena are studied attentively. At the root of all systems of telegraphy, including multiplex systems, there lies the single basic principle upon which their performance depends, namely, the obtaining of a slight mechanical movement at the more or less distant end of a telegraph line. This is accompanied through the utilization of the phenomena of electromagnetism. These phenomena are easy of comprehension and demonstration. If a rod of soft iron be wound around with a number of turns of insulated wire, and a current of electricity be sent through the wire, the rod will be instantly magnetized and will remain a magnet as long as the current flows. But when the current is cut off, the magnetic effect instantly ceases. This device is known as an electromagnet, and the charging and discharging of such a magnet may, of course, be repeated indefinitely, inasmuch a magnet that has the power of attracting to itself pieces of iron or steel, the basic importance of an electromagnet in telegraphy will be at once apparent when we consider the sounder, whose clicks are familiar to every ear. This instrument consists essentially of an electromagnet of horseshoe form, with its two poles close together and with its armature, a bar of iron, maintained in close proximity to the poles, but kept normally in a retracted position by a spring. When the distant operator presses down his key, the circuit is closed and a current passes along the line and through the generally two coils of the electromagnet, thus magnetizing the iron core. Its attractive power draws the armature toward the poles. When the operator releases the pressure on his key, the circuit is broken, current does not flow, the magnetic effect ceases, and the armature is drawn back by its spring. These movements give rise to the clicking sounds which represent the dots and dashes of the Morse or other alphabet as transmitted by the operator. Similar movements, produced in like manner, are availed of in another instrument known as the relay, whose office is to act practically as an automatic transmitter key, repeating the messages received in its coils and sending them on to the next section of the line, equipped with its own battery, or, when the message is intended for its own station, sending the message to an adjacent sounder included in a local battery circuit. With a simple circuit, therefore, between two stations and where an intermediate battery is not necessary, a relay is not used. Passing on to the consideration of another phase of the phenomena of electromagnetism, the reader's attention is called to Figure 1, in which will be seen on the left a simple form of electromagnet consisting of a bar of soft iron wound around with insulated wire through which a current is flowing from a battery. The arrows indicate the direction of flow. All magnets have two poles, north and south. A permanent magnet made of steel, which as distinguished from soft iron retains its magnetism for long periods, is so called because it's permanently magnetized, and its polarity remains fixed. In an electromagnet, the magnetism exists only as long as the current is flowing through the wire, and the polarity of the soft iron bar is determined by the direction of flow of current around it for the time being. If the direction is reversed, the polarity will also be reversed. Assuming, for instance, the bar to be end-on toward the observer, that end will be a south pole if the current is flowing from left to right, clockwise around the bar, or a north pole if flowing in the other direction, as illustrated at the right of the figure. It is immaterial which way wire is wound around the bar, the determining factor of polarity being the direction of the current. It will be clear, therefore, that if two equal currents be passed around a bar in opposite directions, Figure 3, they will tend to produce exactly opposite polarities and thus neutralize each other. Hence the bar would remain non-magnetic. As the path to the quadruplex passes through the duplex, let us consider the Stern's system, after noting one other principle, namely, that if more than one path is presented in which an electric current may complete its circuit, it divides in proportion to the resistance of each path. Hence, if we connect one pole of a battery with the earth, and from the other pole run to the earth two wires of equal resistance as illustrated in Figure 2, equal currents will traverse the wires. The above principles were employed in the Stern's differential duplex system in the following manner. Referring to Figure 3, suppose a wire, A, is led from a battery around a bar of soft iron from left to right, and another wire of equal resistance and equal number of turns, B, around from right to left. The flow of current will cause two equal opposing actions to be set up in the bar. One will exactly offset the other, and no magnetic effect will be produced. A relay thus wound is known as a differential relay, more generally called a neutral relay. The non-technical reader may wonder what use can possibly be made of an apparently non-operative piece of apparatus. It must be borne in mind, however, in considering a duplex system, that a differential relay is used at each end of the line and forms part of the circuit, and that while each relay must be absolutely unresponsive to the signals sent out from its home office, it must respond to signals transmitted by a distant office. Hence the next figure, 4, with its accompanying explanation, will probably make the matter clear. If another battery, D, be introduced at the distant end of the wire A, the differential or neutral relay becomes actively operative as follows. Battery C supplies wires A and B with equal current, but battery D doubles the strength of the current traversing wire A. This is sufficient to not only neutralize the magnetism which the current in wire B would tend to set up, but also by reason of the excess of current in wire A, to make the bar a magnet whose polarity would be determined by the direction of the flow of current around it. In the arrangement shown in Figure 4, the batteries are so connected that current flow is in the same direction, thus doubling the amount of current flowing through wire A. But suppose the batteries were so connected that the current from each set flowed in an opposite direction. The result would be that these currents would oppose and neutralize each other, and therefore none would flow in wire A. Inasmuch, however, as there is nothing to hinder, current would flow from battery C through wire B, and the bar would therefore be magnetized. Hence, assuming that the relay is to be actuated from the distant end, D, it is in a sense immaterial whether the batteries connected with wire A assist or oppose each other, as in either case the bar would be magnetized only through the operation of the distant key. A slight elaboration of Figure 4 will further illustrate the principle of the differential duplex. In Figure 5 are two stations, A, the home end, and B, the distant station to which a message is to be sent. The relay at each end has two coils, 1 and 2, number 1 in each case being known as the main line coil, and 2 as the artificial line coil. The latter in each case has in its circuit a resistance R to compensate for the resistance of the main line, so that there shall be no inequalities in the circuits. The artificial line, as well as that to which the two coils are joined, are connected to earth. There is a battery C and a key K. When the key is depressed, current flows through the relay coils at A, but no magnetism is produced as they oppose each other. The current, however, flows out through the main line coil, over the line, and through the main line coil 1 at B, completing its circuit to earth and magnetizing the bar of the relay, thus causing its armature to be attracted. On releasing the key, the circuit is broken, and magnetism instantly ceases. It will be evident, therefore, that the operator at A may cause the relay at B to act without affecting its own relay. Similar effects would be produced from B to A if the battery and key were placed at the B end. If, therefore, like instruments are placed at each end of a line, as in Figure 6, we have a differential duplex arrangement by means of which two operators may actuate relays at the ends distant from them, without causing the operation of the relays at their home ends. In practice, this is done by means of a special instrument known as a continuity-preserving transmitter, or, usually, as a transmitter. This consists of an electromagnet, T, operated by a key, K, and separate battery. The armature lever, L, is long, pivoted in the center, and is bent over at the end. At a point little beyond its center is a small piece of insulating material to which is screwed a strip of spring metal, S. Conveniently placed with reference to the end of the lever is a bent metallic piece, P. Having contact screw in its upper horizontal arm, and attached to the lower end of this bent piece is a post or standard, to which the main battery is electrically connected. The relay coils are connected by wire to the spring piece S, and the armature lever is connected to earth. If the key is depressed, the armature is attracted and its bent end is moved upward, depressing the spring, which makes contact with the upper screw, which places the battery to the line and simultaneously breaks the ground connection between the spring and the upturned end of the lever, as shown on the left. When the key is released, the battery is again connected to earth. The compensating resistances and condensers necessary for a duplex arrangement are shown in the diagram.
In Figure 6, one transmitter is shown as closed at A, while the other one is open. From our previous illustrations and explanations, it will be readily seen that, with the transmitter closed at station A, current flows via post P through S and to both relay coils at A, thence over the main line to main line coil at B, and down to earth through S and the armature lever with its grounded wire. The relay at A would be unresponsive, but the core of the relay at B would be magnetized and its armature respond to signals from A. In like manner, if the transmitter at B be closed, current would flow through similar parts and thus cause the relay at A to respond. If both transmitters be closed simultaneously, both batteries will be placed to the line, which would practically result in doubling the current in each of the mainline coils, in consequence of which both relays are energized and their armatures attracted through the operation of the keys at the distant ends. Hence, two messages can be sent in opposite directions over the same line simultaneously. The reader will undoubtedly see quite clearly from the above system, which rests upon varying the strength of the current, that the two messages could not be sent in the same direction over the one line at the same time. To accomplish this object, Edison introduced another and distinct feature, namely, the using of the same current but also varying its direction of flow. That is to say, alternately reversing the polarity of the batteries as applied to the line, and thus producing corresponding changes in the polarity of another specially constructed type of relay called a polarized relay. To afford the reader a clear conception of such a relay, we would refer again to Figure 1 and its explanation, from which it appears that the polarity of a soft iron bar is determined not by the strength of the current flowing around it, but by the direction thereof. With this idea clearly in mind, the theory of the polarized relay, generally called polar relay, as presented in the diagram, Figure 7, will be readily understood. As is a bar of soft iron bent as shown and wound around with insulated copper wire, the ends of which are connected with a battery B, thus forming an electromagnet, an essential part of this relay consists of a swinging permanent magnet, C, whose polarity remains fixed, that end between the terminals of the electromagnet being a north pole. Inasmuch as unlike poles of magnets are attracted to each other and like poles repelled, it follows that this north pole will be repelled by the north pole of the electromagnet, but will swing over and be attracted by its south pole. If the direction of flow of current be reversed by reversing the battery, the electromagnetic polarity also reverses and the end of the permanent magnet swings over to the other side. This is shown in the two figures of Figure 7. This device being a relay, its purpose is to repeat transmitted signals into a local circuit, as before explained. For this purpose there are provided at D and E a contact and a backstop, the former of which is opened and closed by the swinging permanent magnet, thus opening and closing the local circuit. Manifestly, there must be provided some convenient way for rapidly transposing the direction of the current flow if such a device as the polar relay is to be used for the reception of telegraph messages, and this is accomplished by means of an instrument called a pole changer, which consists essentially of a movable contact piece connected permanently to the earth or grounded and arranged to connect one or the other pole of a battery to the line and simultaneously ground the other pole. This action of the pole changer is effected by movements of the armature of an electromagnet through the manipulation of an ordinary telegraph key by an operator at the home station, as in the operation of the transmitter above referred to. By a combination of the neutral relay and the polar relay, two operators, by manipulating two telegraph keys in the ordinary way, can simultaneously send two messages over one line in the same direction with the same current, one operator varying its strength and the other operator varying its polarity or direction of flow. This principle was covered by Edison's patent number 162,633 and was known as the Diplex system, although in the patent referred to, Edison showed and claimed the adaptation of the principle to duplex telegraphy. Indeed, as a matter of fact, it was found that by winding the polar relay differently and arranging the circuits and collateral appliances appropriately, the polar duplex system was more highly efficient than the neutral system, and it is extensively used to the present day.
Thus far we have referred to two systems, one the neutral or differential duplex, and the other the combination of the neutral and polar relays, making a diplex system. By one of these two systems, a single wire could be used for sending two messages in opposite directions, and by the other in the same direction or in opposite directions. Edison followed up his work on the diplex and combined the two systems into a quadruplex, by means of which four messages could be sent and received simultaneously over the one wire, two in each direction, thus employing 8 operators, 4 at each end, 2 sending and 2 receiving. The general principles of quadruplex telegraphy are based upon the phenomena which we have briefly outlined in connection with the neutral relay and the polar relay. The equipment of such a system at each end of the line consists of these two instruments, together with the special form of transmitter and the pole changer and their keys for actuating the neutral and polar relays at the other or distant end. Besides these, there are the compensating resistances and condensers. All of these will be seen in the diagram, Figure 8. It will be understood, of course, that the polar relay, as used in the quadruplex system, is wound differently, and therefore its operation is somewhat similar in principle to that of the differentially wound neutral relay, in that it does not respond to the operation of the key at the home office, but only operates in response to the movements of the distant key. Our explanation has merely aimed to show the underlying phenomena and principles in broad outline without entering into more detail than was deemed absolutely necessary. It should be stated, however, that between the outline and the filling in of the details, there was an enormous amount of hard work, study, patient plodding, and endless experiments before Edison finally perfected his quadruplex system in the year 1874. If it were attempted to offer here a detailed explanation of the varied and numerous operations of the quadruplex, this article would assume the proportions of a treatise. An idea of their complexity may be gathered from the following, which is quoted from American Telegraphy and Encyclopedia of the Telegraph by William Mavor, Jr. It may well be doubted whether in the whole range of applied electricity there occur such beautiful combinations, so quickly made, broken up, and others reformed, as in the operation of the Edison quadruplex. For example, it is quite demonstrable that during the making of a simple dash of the Morse alphabet by the neutral relay at the home station, the distant pole changer may reverse its battery several times. The home pole changer may do likewise, and the home transmitter may increase and decrease the electromotive force of the home battery repeatedly. Simultaneously, and of course as a consequence of the foregoing actions, the home neutral relay itself may have had its magnetism reversed several times, and the signal, that is, the dash, will have been made partly by the home battery, partly by the distant and home batteries combined, partly by current on the main line, and partly by current on the artificial line, partly by the main line static current, partly by the condenser static current, and yet on a well-adjusted circuit the dash will have been produced on the quadruplex sounder as clearly as any dash on an ordinary single-wire sounder. We present a diagrammatic illustration of the Edison quadruplex battery key system in Figure 8 and refer the reader to the above or other textbooks if he desires to make a close study of its intricate operations. Before finally dismissing the quadruplex, and for the benefit of the inquiring reader who may vainly puzzle over the intricacies of the circuits shown in Figure 8, a hint as to an essential difference between the neutral relay, as used in the duplex and as used in the quadruplex, may be given. With the duplex, as we have seen, the current on the main line is changed in strength only when both keys at opposite stations are closed together, so that a current due to both batteries flows over the main line. When a single message is sent from one station to the other, or when both stations are sending messages that do not conflict, only one battery or the other is connected to the main line. But with the quadruplex, suppose one of the operators in New York, for instance, is sending reversals of current to Chicago. We can readily see how these changes in polarity will operate the polar relay at the distant station. But why will they not also operate the neutral relay at the distant station as well? This difficulty was solved by dividing the battery at each station into two unequal parts, the smaller battery being always in circuit with the pole changer, ready to have its polarity reversed on the main line to operate the distant polar relay. But the spring retracting the armature of the neutral relay is made so stiff as to resist these weak currents. If, however, the transmitter is operated at the same end, the entire battery is connected to the main line, and the strength of this current is sufficient to operate the neutral relay. Whether the part or all of the battery is alternately connected or disconnected from the main line by the transmitter, the current so varied in strength is subject to reversal of polarity by the pole changer. But the variations in strength have no effect upon the distant polar relay, because that relay, being responsive to changes in polarity of a weak current, is obviously responsive to corresponding changes in polarity of a powerful current. With this distinction before him, the reader will have no difficulty in following the circuits of Figure 8, bearing always in mind that by reason of the differential winding of the polar and neutral relays, neither of the relays at one station will respond to the home battery and can only respond to the distant battery, the polar relay responding when the polarity of the current is reversed, whether the current be strong or weak, and the neutral relay responding when the line current is increased, regardless of its polarity. It should be added that besides the system illustrated in Figure 8, which is known as the differential principle, the quadruplex was also arranged to operate on the Wheatstone bridge principle, but it is not deemed necessary to enter into its details. The underlying phenomena were similar, the difference consisting largely in the arrangement of the circuits and apparatus. Edison made another notable contribution to multiplex telegraphy some years later in the Phonoplex. The name suggests the use of the telephone, and such indeed is the case. The necessity for this invention arose out of the problem of increasing the capacity of telegraph lines employed in through and way service, such as upon railroads. In a railroad system there are usually two terminal stations and a number of way stations.
There is naturally much intercommunication, which would be greatly curtailed by a system having the capacity of only a single message at a time. The duplexes above described could not be used on a railroad telegraph system because of the necessity of electrically balancing the line, which, while entirely feasible on a through line, would not be practicable between a number of intercommunicating points. Edison's Phonoplex normally doubled the capacity of telegraph lines, whether employed on way business or through traffic, but in actual practice made it possible to obtain more than double service. It has been in practical use for many years on some of the leading railroads of the United States. The system is a combination of telegraphic apparatus and telephone receiver, although in this case the latter instrument is not used in the generally understood manner. It is well known that the diaphragm of a telephone vibrates with the fluctuations of the current energizing the magnet beneath it. If the make and break of the magnetizing current be rapid, the vibrations being within the limits of the human ear, the diaphragm will produce an audible sound. But if the make and break be as slow as with the ordinary Morse transmission, the diaphragm will be merely flexed and return to its original form without producing a sound. If, therefore, there be placed in the same circuit a regular telegraph relay and a special telephone, an operator may, by manipulating a key, operate the relay and its sounder without producing a sound in the telephone, as the makes and breaks of the key are far below the limit of audibility. But if through the same circuit by means of another key suitably connected there sent the rapid changes in current from an induction coil, it will cause a series of loud clicks in the telephone, corresponding to the signals transmitted, but this current is too weak to affect the telegraph relay. It will be seen, therefore, that this method of weak duplexing is practiced, not by varying the strength or polarity, but by sending two kinds of current over the wire. Thus, two sets of Morse signals can be transmitted by two operators over one line at the same time without interfering with each other, and not only between terminal offices, but also between a terminal office and any intermediate office, or between two intermediate offices alone. End of Appendix 2. Recording by Anna Maria Viola. www.amvaudio.com